Hello. In this video we're going to take a look at angular momentum again, but this time using ladder operators. Quite a neat trick for evaluating some of the properties that we derived in length in a previous video. So we've seen that the commutator of angular momentum operators is as follows. Commutator of Lx with Ly is equal to IH bar Lz, and the etc. here just indicates that you can take cyclic permutations of x, y, and z to arrive at equivalent results for the other two cases. And it's convenient to define the following operators. L plus and minus equal by definition to Lx plus or minus ILy. So if we look at these operators and their commutators with the remaining terms, we find the following. So L plus or minus with Lz commutator, we can expand it to Lx commutator with Lz plus or minus I times Ly commutator with Lz. We can substitute the various forms of this expression into these two places to find the result. So we find this, but this can be factored into the form where we've got the L plus or minus back again. And so the final result, the commutator of L plus or minus with Lz is equal to minus plus H bar L plus or minus. Let's box that. So the reason this is convenient is that we've seen previously that we can define eigenstates of the Lz operator as follows. So Lz acting on state m, where m is an integer, m is not related to the mass at all, it's just an integer, and this is a conventional label, which is a little bit unfortunate because of the confusion with mass, is equal to h bar m, same integer, multiplying the state m. So let's look at what happens when we act on both sides of this with L plus or minus. So on the left-hand side we have L plus or minus acting on Lz, acting on m as before. Then we have on the right-hand side h bar m, the L plus or minus comes through and acts on the state. So over here we'd like to commute the Lz through the L plus or minus. And I should say that when I'm writing L plus or minus, of course, this is two separate operators. One is L plus with a plus sign here, and one is L minus with a minus sign here. We're just saving ourselves some time by doing both at once with a convenient notation. So we can pull the Lz through the L plus or minus as follows. That is, we can write Lz to the left of L plus or minus, added to the commutator of L plus or minus with Lz, because the second term of this is minus Lz L plus minus, which cancels this one. The first term is L plus or minus Lz, which is the thing we started with. This commutator we've just found as follows. We can take this term over to the other side to get the end result. So Lz acting on the state inside the parentheses here is equal to h bar m plus or minus 1 acting on the same state inside the parentheses. And so m by definition was an eigenstate of Lz with eigenvalue h bar m. And so L plus or minus acting on the state m must also be an eigenstate, because just ignoring what's written inside the parentheses, this remaining thing is an eigenvalue equation for Lz. And so this must also be an eigenstate, and the eigenvalue must be h bar m plus or minus 1. So you see that L plus acting on state m raises the eigenvalue by 1, or h bar times 1, and L minus lowers it again. And so these L plus or minus are angular momentum raising and lowering operators, or angular momentum ladder operators. So if you recall from the previous video that Lx, Ly, and Lz, while they don't commute with one another, they all commute with L squared, the square of the angular momentum operator. And so that fact tells us that L plus or minus must also commute with L squared, because L plus or minus are just a linear combination of Lx and Ly, and each of these individually commutes with L squared. So we have this. So the commutator of these two is 0. And that means that recalling the eigenvalue equations for L squared, so just to recap that we can pick one of the three, x, y, or z, and have a well-defined angular momentum in that direction, and we can have that simultaneously with knowledge of the eigenvalue of L squared. So we write the eigenvalue equations as follows. That is, we can define some state L comma m, where L and m are good quantum numbers simultaneously. Lz acting on this state gives us h bar m, L comma m, just like we saw up here. And L squared acting on L comma m returns an eigenvalue associated with L squared, which it turns out is best written as h bar squared L plus 1, where L is an integer. And so the point of noting that L plus or minus commute with L squared means that when we raise or lower m, the eigenvalue associated with Lz, the z projection of the angular momentum, because after all that's what these components are, this doesn't affect the value of little l, that is the eigenvalue associated with L squared, the total angular momentum squared. So taking this all into account, we can see on this basis that L squared is the square of the length of the angular momentum. That's certainly what it would be classically. We can think of it like that quantum mechanically as well, or rather we can think of the corresponding eigenvalues that way. And so this is conserved when we raise or lower m, the z projection of angular momentum. And since these L plus or minus are forming, taking us up or down a ladder of states, we can see that that ladder should have both a top and a bottom defined by the the total length of the angular momentum vector. Putting this all together, we deduce the following. So given that L, the eigenvalue associated with the L squared, the total angular momentum squared, this is an integer and it's greater than or equal to 0, because you can think of the total length of the angular momentum operator squared as corresponding to the quantum version of the length squared of the angular momentum. So clearly it's got to be 0 or greater. And then m, which corresponds to the z projection of the angular momentum, is also an integer, and it must fall between minus L and L. So what we've seen is that, and we can just think about this physically, because we have L squared corresponding to the length squared of some vector. Admittedly, it's like a quantum operator associated with the angular momentum, but it is nevertheless telling us something about some kind of quantum spinning particle. So the length, it has some total value, and so the z projection, as in the projection along some direction, can't be any bigger than the length of the vector itself. Okay, so that intuition still holds in this quantum case. And so what we see in terms of these raising and lowering operators is that unlike the harmonic oscillator case, where we had a ground state and then an infinite number of rungs above that state, evenly spaced in energy, in this case we have the following scenario. So we start with the case L equals 2, which is considered this case. So our LM ket has L equals 2 in each entry. Then our values of m can range from -2 up to 2. And to go up the rungs of this ladder, we use the L plus, the angular momentum raising operator. We can do that repeatedly. And to go back down, we use L minus, like so. But remember, when we studied the raising and lowering operators for the harmonic oscillator, if we used the lowering operator on the ground state, we got 0. And it's not the state 0, it's the number 0. We literally just got 0. Now that's true here as well. If we try to lower off the bottom of the ladder, we get 0 again. But actually this time, if we try to raise off the top of the ladder, we also get 0. So the ladder has a finite number of rungs, which you can think about physically just because you can't get a larger z projection than the total length of the vector. And so that's kind of what's happening here. So we now have a ladder with a finite number of rungs, where the number of rungs is specified by L, the quantum number associated with the L squared total angular momentum squared operator. Okay, thank you for your time.